Section 3.6, we're looking at sigma notation. If you've not met it before, this symbol here is a sigma, and you probably have met it before if you've ever used a spreadsheet, because an Excel spreadsheet at least, because Excel spreadsheets have this as the sum symbol. It adds up all the numbers in a column or a row, and that's what it means. It means add up. So the way the notation works mathematically would be, let's take a nice example to start with. The sum from r equals 1 to 6 of 2r plus 1. That's how we'd read this. Now, the letter at the bottom here tells you which letter to change. So here, there's only one letter in the expression, but we could have something like this. R equals 1 to 6 of r times x plus 3, for example. Now, in this case, that would tell us that, well, let's do this example and then see how it works out here. But it's important that we have an r down here. We're going to start with r equals 1. I'm going to substitute it into here. So 2 times 1 plus 1 is 3. Then we're going to make r equal to 2. So 2 times 2 plus 1. So it's just like having an nth term formula, only we're using an r instead of an n. Doesn't matter that we're using an r instead of an n, it's still the same thing. When r equals 3, we get 7. And we're not just going to write it down. This sigma tells us it's a sum, so we're going to add these up. So 3 plus 5 plus 7, and we're going to keep going. Now, when do we stop? Well, the number on top tells us when to stop. So we start with r equals 1. We finish when we get to r equals 6. So 1, 2, 3, 4, 5, 6. So that there means add together those 6 numbers. The number that you get when r equals 1, when r equals 2, when r equals 3, 4, 5, and 6. Add them all up, then we get that. So how does that compare to this? Well, here, look, this expression has got 2 different letters in it. The letter that we've written down here is the letter that we change. So we start with r equals 1, then we add to that when r equals 2, then we add to that when r equals 3, and so on. Okay, so I'm not going to change the x, it's the letter down here that I change. Now, if we've got an expression like this, where there is only one letter in the expression, sometimes we'll cheat and we'll write that as sum from 1 to 6 as 2r plus 1. Okay, so sometimes you'll see that written, which is just, saving a little bit of time. There's only one letter, so it's kind of obviously the r that changes its value. But we shouldn't, strictly speaking, do that, and here's why. I can say sum from r equals 1 to 4 of x. Well, there's only one letter here, but r is the thing that I'm changing. So what does that look like? Well, when r equals 1, this expression has got the value of x. Because there's no r in it, it's not dependent on r, this expression is an x. When r equals 2, this expression gets the value x. When r equals 3, x. When r equals 4, x. So sum from r equals 1 to 4 of x is x plus x, which is 4 lots of x. Okay? So strictly speaking, we shouldn't cheat and just say sum from 1 to 6 or something like that, because if I missed out the r there, you might think that I was telling you to do 1 plus 2 plus 3 plus 4. Actually, we're telling you to do x plus x plus x plus x. That leads us to something it says in the book, which is this. Sum from r equals 1 to n of 1 tells us, well, when r equals 1, this expression takes the value 1. When r equals 2, this expression takes the value 1. So it's just doing 1 added together n times. So in other words, n. So because when do we stop? We stop when we get to r equals n. So we're going to write down 1 n times in a row. Okay. So hopefully you're getting the pattern for how these sums work now. We let r tick through the numbers 1, 2, 3, and so on, and you stop when r gets to the number on the top. Let's have another example. Sum from r equals 1 to n of r. Well, that is r equals 1. When r equals 2, this expression here is just r, so it's 2. When r is 3, when r is 4, when r is 5. So in other words, that is the triangular numbers, isn't it? So we know that as n over 2, n plus 1. Okay? And if we go back to that first example, this here is an arithmetic progression, so that will be the sum of the first 6 terms of this is 6 over 2, 2 times the first term, which is 3, plus n minus 1, which is 5, lots of d, and d is 2. Okay, so that's the Sn equals n over 2, 2a plus n minus 1 d formula. Okay, so if we want to find sum from 1 to 6 of this expression here, we write the sequence down, we write the series down, and we find out that series is actually an arithmetic progression, and then we can use the formula. Okay. In other cases, you're going to write the series down and find it's not an arithmetic progression, it's not a geometric progression, so you're going to have to maybe just do it by hand, add together 6 numbers, shouldn't be too bad. So what do we need to do with this? So in example on 17 and 18, we should have enough information really for exercise 3F now, but let's just double check. Sum from 1 to 20 of 4r plus 1. Well, this series is, well, when r equals 1 you get 5, when r equals 2 you get 9, when r equals 3 you get 13, so it is that sequence. That is an arithmetic progression, and we maybe recognised it because this is the nth term for an arithmetic progression, kind of a formula, isn't it? Okay, it's a linear expression. So we can work that out with our arithmetic progression sum to n terms formula. With this one, when k this time, k is 1, k is 2, k is 3, we get this sequence. And again, you look at that and you think, well, hopefully we recognise that that is the expression for the nth term, or in this case the kth term, of a geometric progression. So if we want to add together the first 12 terms, we want S12, which is this thing here. Okay. Now, there's several clever things we can do with this notation, and the first one that we're going to see is this: sum from k equals 5 to 12 of 5 times 3k minus 1. So that thing there is asking you, well, start with k equals 5. Don't start with k equals 1. So you start at 5 times 3 to the power of 4. Then you do 5 times 3 to the power of 5, and then 5 times 3 to the power of 6, and you keep going till you get to k equals 12. So you keep going, you add all these up until you get to 5 times 3 to the power of 11. Okay, so we'd add those things up. Now, that's a tricky thing to do, except, now if you understand why this is true straight away, then you've understood the idea of this. I taught this to my class yesterday and managed to write the wrong thing on the board, which confused, well, actually, they understood it, it confused me. So let me try and not write the wrong thing here. So, sum from k equals 1 to 12 of 5 times 3k minus 1, take away the sum from k equals 1 to 4 of 5 times 3 to the k minus 1. Okay, so can we see this? This says add together the first 12 terms. This says add together the first 4 terms. If you do the first 12 terms, take away the first 4 terms, you're going to get the terms from 5 to 12. Okay. Now this thing is the first 12 terms of an a geometric progression. So you can do that as the Sn formula that we know, a times 1 minus r to the n, and da da da. This one is the first 4 terms, so you can do that as an Sn formula as well. So we can calculate this, we can calculate this, we can do a takeaway, and that's going to be easier than finding those 7 different numbers with powers of 3 in that get bigger and bigger, and then trying to add them all up. So they mean the same thing, but there's a shortcut way of getting there. Okay, I think that is everything we can do with sigma notation. Get used to it. It's gonna be around to stay. We use it in lots of different areas of maths, and it's a really handy notation. It's a bit fiddly at first, but with a bit of practice, I'm sure you'll get there.